Good morning, Flemmis. Welcome back to another video. So I've had this thing for an extensive amount of time already in my folder, but I never really made a video on that because, well, the solution isn't something that most people like. It has to do with the arrow function, but I'm still going to put it here on my YouTube channel because why the hell not? So Laplace transform of e to negative t squared, of a Gaussian curve, you could say, and of a Gaussian bell curve in this case. And this thing actually converges because of the negative sign right here. If you would have a positive t squared, then this wouldn't even converge. So yeah, for e to the t squared, it wouldn't converge, but in this case, it does converge. So let's just use the definition of Laplace transform on this thing and see what we actually get. So that's the integral from 0 to infinity, 1 infinity krill, because the integral is the krill and the sum is the boy, you see? So e to the negative t squared, e to the negative s times t, folder, but I never really Good morning, Flemmis. Welcome back to another video. So I've had this thing for an extensive amount of time already in my folder, but I never really made a video on that because, well, the solution isn't something that most people like. It has to do with the arrow function, but I'm still going to put it here on my YouTube channel because why the hell not? So Laplace transform of e to negative t squared, of a Gaussian curve, you could say, and of a Gaussian bell curve in this case. And this thing actually converges because of the negative sign right here. If you would have a positive t squared, then this wouldn't even converge. So yeah, for e to the t squared, it wouldn't converge, but in this case, it does converge. So let's just use the definition of Laplace transform on this thing and see what we actually get. So that's the integral from 0 to infinity, 1 infinity krill, because the integral is the krill and the sum is the boy, you see? So e to the negative t squared, e to the negative s times t, integrated with respect to t. And you might notice the exponential function is a nice functional equation on the real and complex numbers, so we can actually bring this together and add our exponents together, meaning we can actually factor stuff out right here. So we are going to get an integral from 0 to infinity. I'm terribly sorry for the blue chalk, but I have to get rid of this. This is just, he shouldn't be on this channel.
Con Grammarly puedes escribir en inglés rápido y confiadamente. Controla tus correos.
To become positive, so e to the positive, because it must be squared, we are going to get a squared plus 2ab plus b squared. Okay, all of you should know this, otherwise you shouldn't be on this channel if you don't even know this thing right there. So meaning if we interpret our s times t as nothing but 2 times s over 2 times t, we actually get our factor of 2 right here, and we can identify our b as being nothing but s over 2. So the thing here right now is we can just add our b squared to it. We can just add another 0 to it, because if you have one apple and you don't place another apple next to it, you still have only one apple. So that's our apple, and we are not going to place any other apple next to it, meaning we are going to add our b squared to it, which is nothing but s squared over 2 squared, and then we are going to subtract it right again. So this is s squared over 4. Now, this thing right here is exactly our a plus b squared, meaning this is nothing but t plus s over 2, but the whole thing squared, minus s squared over 4. That's what you guys call completing the square. I think I made a video on that. I'm not really sure. Yeah, I made videos in German and English on that actually. So we can plug this stuff into here. That's quite the same expression. So integral from 0 to infinity. That's quite a beautiful integral sign right here. So we are going to get e to the negative t plus s over 2 squared. And now using the property that we have a functional equation on the exponential function right here, negative and negative is going to become positive. So e to the positive s squared over 4 integrated with respect to t. And if you're a smart boy, a smart bruh, or there was an epic bruh moment bruh, you can actually bring this to the outside because in terms of t, e to the s squared over 4 is just a constant, so let's bring it to the outside. So that's nothing but e to the s squared over 4, and now an integral. And integrating this is still not quite easy, maybe also not intuitive on first sight, so let's introduce a little substitution. So for example, let tau be equal to exactly this argument right here, so t plus s over 2. If we differentiate that, we are going to end up with dt being nothing but d tau. Okay, so we can plug this into here. What about the lower bound? So if we plug 0 into here, that's going to be s over 2. And this is where already one problem comes in. Otherwise, this would be integrable pretty easily, kind of. I made several videos on this very integral. And if we let t go to infinity, tau also goes to infinity. This is going to give us e to the negative tau squared integrated with respect to tau. Now you could say that we are basically done, because this thing right here is by definition some analytical function. Namely, we can identify this as, this is nothing but, let me think, so we should get a factor of what, yeah, okay, this is square root of pi over 2 times the complementary arrow function of s over 2. Okay, this is the reason why I didn't make a video on that up until now, because this thing right here isn't something really intuitive. It just pops up. It's a really special function, and that's why I didn't make the video on that right here right now. I wonder if this factor is okay. Yeah, in a normal case you would have 2 over square root of pi times this, because if you evaluate this from 0 to infinity, you are going to get square root of pi over 2, and it's going to be a 1. Yeah, right, so the arrow function, the complementary arrow function of 0 would be just 1, and that's why we get this factor of square root of pi over 2. Okay, I just had to think about it, I don't want to make any mistakes. But you can take kind of a different approach, namely using the Taylor series on this thing right here. That's why I'm making the video now, because we talked about Taylor series, meaning if we still have this Laplace transform, that's e to the s squared over 4 times, okay, integral from s over 2 to infinity. And now for the Taylor series expansion of this thing right here, I just thought that my microphone dropped off. That's why I was looking down. Hello, boys and girls. So this thing as a Taylor series, we have talked about this several times. It's nothing but the infinity boy running from 0 to infinity. That's not a 6. That's supposed to be a 0 of, okay, -1 to the kth power. Okay, and then we are going to get tau squared to the kth power, which is nothing but tau to the 2k power over k factorial integrated with respect to tau. Okay, this is what we get right here at the moment. And you see, our exponential function, so also our e to the negative tau squared, has an infinite radius of convergence. I have proven this fact before. Meaning on this very interval, our Taylor series expansion converges uniformly and absolutely, meaning overall we can interchange this limit and this limit, so the summation and the integration, and we can just integrate this polynomial. Also we can bring this factor right here, this constant, to the outside together with the summation to end up with a beautiful e to the s squared over 4. Then the infinity boy, from k equals to 0 to infinity. -1 to the kth power over k factorial, and now times the integral s over 2 to infinity tau to the 2kth power integrated with respect to tau. And integrating a polynomial is actually quite easy. So this is going to give us tau to the 2k plus 1th power over 2k plus 1. Now we have to evaluate it from s over 2 to infinity. And this is where another problem comes in. You can just solve this thing right here numerically. It doesn't have a nice closed form. I can't really say anything about it. Post some comments what restrictions we have to place on s here actually. I think s can be any real number, so it doesn't quite matter if you have a negative number right here, ss, so the real part really doesn't have any restrictions. I could be wrong on this part. Please tell me if I'm right on this part or not. Leave some comments down below. And yeah, I don't know about the imaginary part of s. So yeah, I don't want to place any restrictions right here on s right now. It's just a number. So yeah, it could be any real number probably. So overall, we can also express our Laplace transform as nothing but e to the s squared over 4. Then we have the infinity boy, running from k being equal to 0 to infinity of -1 to to the kth power tau to the 2k plus 1th power over k factorial times 2k plus 1, evaluated from s over 2 to infinity. And one cool thing is, you now know what the Taylor series expansion of our complementary arrow function actually is. Or our arrow function in itself. It depends on the upper and lower bounds if it is complementary or the arrow function in itself. And this is basically it. So I know this answer is not going to be satisfactory for all of you guys, but it is what it is. Sometimes mathematics is just numeric stuff and you can find a nice closed form like e or pi or I don't know, the oily macaroni constant. Never mind, if you did enjoy this video, please like and subscribe and recommend the channel if you like, if you want to support the channel a bit more. By those t-shirts I created, I'm not wearing one of those at the moment. And also, click on those questions I post from time to time on Quora. And up until the next video, have a flammable day. My mouth is running dry. Maybe you can hear it. And yeah, I'm going to drink something now. And up until the next video, have a flammable day. See ya. Du kannst. Hier am besten, oder? Hier ist eigentlich eine gute Stelle.
Desinfecta todos tus objetos con Sansón sanitizante.
El chis chis para todo.
New challenger approaching.
I guess the boys are coming finally. Good morning, fellow mathematicians. Welcome back to another video. There are people on the floor above me and they are loud as fuck. So I had to delete the first video I made on this one because they were so annoying. I hope they will stop with that soon. In the next 3 videos we are going to talk about this integral right here, this improper one from minus infinity to infinity of cosine of x over x.